Welcome to the second part of the sensitivity analysis using graphical approach. So in the previous video, we've seen the effects of changing the coefficients of our objective function. Now we are going to see the change in the right-hand side of the constraints. Just a quick review on what we've seen on the previous video. We changed the price of the soldier, which is originally $3, and then we saw that this kind of change affects the gradient of the isoprofit line. Now we are going to change the right-hand side value of a constraint and then see how it affects the current optimal solution. So for example, we are going to change the value of the availability of finishing hour, which is currently we have 100 hours of finishing. Now this change will affect this line, the finishing constraint line, because the right hand side currently is 100, and then when we change it, of course this line will change as well. So we are going to change the constraint of the finishing, and you see that it will affect our feasible region. One thing to notice or to observe here is that the current solution happens when the carpentry and finishing constraints are binding. So you see that the point B here is the intersection of the finishing constraint and the carpentry constraint. Because it is the intersection, you can say that both constraints are binding at point B. Binding means that the sign here between the left hand side and the right hand side becomes equality. Similar to before, this is the question that we'd like to answer. What value of finishing hour that keeps the current basis optimal? So basis is a set of basic variables. So we'd like to see how much the finishing hour may change such that the current basis remains optimal. Recall our observation before that the current basis, or the point B, is the intersection of the finishing and carpentry constraint. So if I shift this finishing constraint line to the left and it goes too far to the left, the current basis is no longer in the feasible region. Because if you shift this line far to the left, the intersection between finishing and carpentry will fall outside of the feasible region. So here's the original finishing constraint, and then I shift it to the left. If I go far to the left, then you see now the intersection between the new finishing constraint and the carpentry constraint falls outside of the feasible region. In other words, it cannot be an optimal solution anymore, because in the first place it is not even feasible, right? So you see here that if we shift the finishing lines too far to the left, then the current basis is no longer optimal. Now, if you think about it, if you shift the finishing constraint to the right and it goes too far to the right, same as before, the intersection between finishing and carpentry will fall outside of the feasible region. So that is the current finishing constraint, and then I shift it to the right, and I go too far to the right, and now you can see that the new intersection between the new finishing constraint and the carpentry constraint happens outside of the feasible region. Same as before, we try to be more and more specific. So we go too far to the left means that we can say we go farther left than the point A. So you can shift the finishing constraint to the left as long as you do not pass this A line. Past this A point. Similarly, you may go to the right, so you shift this finishing constraint to the right as long as you do not pass this D point. So if you go farther than A, farther to the left than A, farther to the right than D, then the current basis is no longer optimal. So the current position is when we have the right hand side equals 100. Now we have seen from the previous slide, when we shift the finishing constraints farther left than A or farther right than D, then the current basis is no longer optimal because the intersection between finishing and carpentry will fall outside of the feasible region. Okay, so what is the right hand side value if we want to go farther left than A? Well, you can just plug in this point A, 0.80, to this equation, 2x1 plus x2. 2 times 0 plus 80 equals 80. So when your right hand side B1 is less than 80, you will go farther left than the point A. Similarly, you will go farther right than point D if your B1 is greater than 120. So the point D is 40.40. You plug into 2x1 plus x2, you will get the value of the right hand side 140. Any value that is greater than 120 will makes the finishing constraint goes farther right than point D. So in other words, the current basis remains optimal or does not change when B1 is between 80 and 120, including 80 and 120. We've seen from the previous slide that the current basis does not change when B1 is between 80 and 120. But it doesn't mean that the X value and the Z value does not change as well. Because when you shift the finishing constraint line, your feasible region change, so of course the value of your X will change as well. Okay, so please distinguish between the current optimal basis does not change and the value of X itself, it does change. Okay, so first observation that we've made is that the current optimal basis happens when the finishing and carpentry constraint are binding. So we may apply the change between the boundaries. So we may change the value of B1 between minus 20 and plus 20, right? Because the current value is 100. We may go down to 80, means that our delta can be minus 20. We can go up to 120, means that our delta 1 or our change can go up to positive 20. Now let's go back to this fact that both are binding. So this is the finishing constraint, this is the carpentry constraint. Now what you do is you put this change on the right hand side of the finishing. So originally it is just 100, now you say 100 plus delta 1, where delta 1 must be between minus 20 and plus 20. Now you do the elimination and then you find out that the value of x1 and x2, they look like this, okay? As long as delta is between minus 20 and 20. So those are the values of x. Of course, if delta 1 equals 0, you will get x1 equal 20, x2 equals 60, which is the point B in our current solution. Now, once you have the x1 and x2, you may compute the value of the new z using the equation of 3x1 plus 2x2. Now that was for the finishing constraint. Now you may perform similar analysis for the carpentry constraint. In other words, we are going to see how much you can change B2 such that the current basis remains optimal. Similar to before, you may shift the carpentry constraint as long as it does not go up farther than this point and it doesn't go farther down than the point C. Similar reasoning, because if you go farther up than this point, the intersection between finishing and carpentry will fall outside of the feasible region. Same here, if you go lower than the point C, the intersection between carpentry and finishing happens outside of the feasible region. So if you do the analysis, you will obtain that as long as B2 is between 60 and 100, then the current basis does not change. However, remember the value of X changes. So here, same as before, we observe that finishing and carpentry are binding. So let's apply the change between the allowable boundaries. Same as before, the current value is 80 for B2. We may go down minus 20. We may go up by 20 because the boundary is between 60 and 100. So apply the delta 2 in the correct position in the constraint of the carpentry, and then you perform the elimination, and then you see that these are the values for x1 and x2. Same as before, you may check if delta 2 equals 0. The solution is x1 equals 20, x2 equals 60, which is exactly the point B itself. So those are the values for x, and then same as before, if you want to get the value of z, you just plug in the value of x1 and x2 with the delta to the equation 3x1 plus 2x2. And then if you have the value of the delta, then you just replace delta 2 with the value that you want. Now it's quite interesting for the third constraint because it is not binding. So you see that this is the demand constraint, it is not binding. So as long as this B3 is greater than 20, it will not disturb the current basis, right? So if this is 40, this is here, is okay. Finishing and carpentry are still binding. If it is 35, let's say it's still okay. If it is 25, it's still okay. If it is exactly 20, it's still okay because the intersection between finishing and carpentry is still feasible. It is not okay if B3 equals, let's say, 10 or something, right? Because if B3 equals 10, it's here, it will make the intersection between finishing and carpentry falls outside of the feasible region. However, if B3, let's say, is 60 or 80, it is still okay. So we get the value of B3 is as long as B3 is greater than or equals to 20, or 20 is less than or equals to B3, the current basis remains optimal. This is our current basis, it just involves finishing and carpentry constraints. So when we apply the change, in which delta 3 is greater than or equals to minus 20, we can see that delta 3 does not affect our equations because this is about finishing, this is about carpentry. So delta 3 is about demand, so of course it is not involved in these two values here. So you can see that as long as delta 3 is greater than or equals to minus 20, our basis remains optimal, and in this case the value of x1, the value of x2, they remain the same. Why? Because the demand constraint is not binding at the current optimal basis. And the same as before, you may recompute the z value, although in this case that does not change. The z value will always be 3 times 20 plus 2 times 60 equals 180 as long as delta 3 is within this boundary. Now, why sensitivity analysis is important? Because the value of the parameters may change in reality. If we have done sensitivity analysis, sometimes we know that we do not need to resolve the entire problem, right? For example, if the price of the soldier toy change a little bit, we know that our current basis remains optimal, so we do not need to resolve the entire problem. We may still need to recompute the x value and the z values though. Also, the value of the parameters itself may be naturally uncertain. For example, the demand, you cannot really say that the demand is always less than or equals to 40. Maybe it is 40, maybe it is 39, 35, and so on. But from the sensitivity analysis, we know that, for example, in a Gyapeto problem, as long as the demand is 20 units or more, then the current basis remains optimal. In this case of the demand in the Gyapeto example, if the demand is greater than 20, then the x value of x1, x2, they remain exactly the same. So this is why sensitivity analysis is useful. Okay, so here are some questions to check your understanding. As usual, I will give you a pause on the video and then I will give you the answer after the pause on the video. So the current B1 or the right hand side value of the finishing constraint is 100. And then we have obtained the boundaries for B1 between 80 and 120 such that the current optimal basis does not change. So the question is, if B1 changes to 87, currently 100, it changes to 87, then what is the value of delta 1? Okay, so here are the answer is minus 13 because the current value of B1 is 100. If we go down to 87, it means delta 1 equals minus 13. Now suppose B1 changes to 117, then what is the value of delta 1? The answer is 17 because we go up from the current value 100 up to 117. Now if B1 changes to 117, then what is the value of x1, x2, and z? If B1 equals 117, means that delta 1 equals 17. From here we can see that x1 equals 20 plus delta 1, so 20 plus 17 equals 37. x2 equals 60 minus delta 1, so 60 minus 17 equals 43, and then you may compute the z, the new z value using this equation, 3x1 plus 2x2. Now here's the last question. If B1 changes to 127, then what is the new value of x1, x2, and z? So because 127 is outside of the allowable B1 value, it changes from 100 to 127. So the delta is plus 27, which is outside of this boundary. So we know that the current basis is no longer optimal, which means that we cannot use this calculation here to compute the new value of x1 and x2. Because the current basis is no longer optimal, we need to resolve the problem using simplex algorithm. So that's the end of this part where we look at the graphical approach to see how we may perform sensitivity analysis. In the next video, we're going to look at a new term which is called shadow price. So see you on the next one, and thank you.